Hi guys, and welcome to JP Academia. Light serves as an important element in our daily lives. It is a sensory input to our brain to detect visual patterns. It also plays an important role in health, communication, energy, design, and in other fields as well. In this video lecture, I will discuss how to manipulate light using mirrors and lenses. Let's start. And this is the outline of this video lecture. I will start by introducing first what is a visible light. Visible light is just a small portion of the electromagnetic spectrum. In a vacuum, all the electromagnetic radiation travels at the speed c, this one, which is equal to about 3 times 10 to the 8 meters per second. However, the effective speed of light becomes slower in a material medium, and this is quantified in terms of the index of refraction, this one, for that specific medium. The refractive index n is just the speed of light in vacuum, so that's c, over the speed of light in a medium v. In discussing the propagation of light, there are different phenomena that affects it. It includes the following. So first we have reflection, which happens usually when a light is incident on a surface. Next we have refraction, or this refers to the bending of light wave as it enters a medium here, and its speed is different. Diffraction, this one, this is the bending of light waves due to an obstacle, and wave spreading is observed in small openings. Last, we have the interference, in which two coherent waves overlap to generate a resultant wave. Light source, such as a functioning light bulb, or let's say the sun, are observed by the light emitted by them. On the other hand, we can see most objects due to the reflected light on its surface. The concept of reflection is important in discussing mirrors. Let's start with a plane mirror. So I have here a plane mirror with an object O in front of it. Then we have here the rays, this one. So the rays coming from the top portion of the object shown. But please take note that in reality, light rays come from all parts of the object. According to the law of reflection, incident angle is equal to the reflected angle. Note that the angle of incidence, this one, is between the ray and the normal to the surface, while the angle of reflection is between the reflected ray and the normal. These rays will appear to come from a point I in the image seen at the opposite side of the mirror. Note that the light cannot pass through the mirror, so it's purely reflection. For a plane mirror, the image formed behind a mirror is always virtual, meaning the light does not come from the image. In terms of size, as can be observed, the image size is equal to the object size. Last, the object distance is equal to the image distance. Next, we will discuss spherical mirrors, or sometimes it is also called the curved mirrors. It's important for us to understand the parts of spherical mirrors, especially when we are going to discuss the image that will be formed using these mirrors. So first, we have here the principal axis. This one, the principal axis, the one in the broken green line. This is the line that passes through the center of the sphere. So let's imagine that this will form a sphere. We have here the convex mirror. Then at the right side, we have the concave mirror, this one. Next, we have the center of curvature C, this one. This is the point in the center of the sphere from which the mirror is formed. Next part is the principal focus, or focus F, capital F. This refers to the midway point between the point P, this one, and the center of curvature C. In my drawing, note that the distance PF, so this distance, is equal to the distance FC. Okay. Next part, we have the radius of curvature, capital R, and this is the distance between the point P and the center of curvature. While the focal length, small f, this one, this refers to the distance from the point P to the focal point capital F. Note here that the radius of curvature R is 2 times the focal length F. So therefore, R is equal to 2F for this scenario. Last, I want to point out two spherical mirrors in this illustration. First, we have the convex mirror, this one. And this is also called the diverging mirror because when we have this incoming parallel light rays, it will diverge the light as can be observed in my drawing. Second, we have the concave mirror at the right. This is also called the converging mirror because when we have this incoming parallel light rays, this will converge or the light will converge to the focus F. So next, if we want to find the position and characteristic of the form image, it can be its size and orientation relative to the object, we can use the ray diagram. For mirrors, it is drawn based off the law of reflection. I have here an illustration specific for a plane mirror. First step is to draw at least two rays from the object O. So this is our object O. Then we have these two light rays as the incident light rays that will strike the mirror. Then following the law of reflection, draw the normal to the surface, forming 90 degrees to the mirror surface. Then draw the reflected rays relative to the normal lines, making sure that we follow the law of reflection in terms of the angle of incidence and angle of reflection. Next step is to extend the rays of the reflection until they meet behind the mirror as shown here. So I have extended this reflected rays. Mark the point where the rays meet, and that is the image form for this scenario. For plane mirror, it is always a virtual image, this one, same size, and last, the object distance is equal to the image distance. Okay, next, let's try a convex mirror. Initial step is to place the object on the principal axis in front of the mirror. So this is the front of the mirror. The back is the one with the shade. Mark the important parts including the center of curvature C, principal focus F, and the point P. These labels will guide you in your ray tracing. First step for the ray tracing is to draw a line from the top of the object going to the focus of this convex mirror, taking note that the light cannot pass through this mirror. So this will generate a reflected ray, this one, parallel to the principal axis as shown. So this is in parallel with this. Second, so this is the second one, draw another line, this time parallel to the principal axis from the object to the surface of the mirror. Then for the convex mirror, this parallel ray will be reflected outwards relative to the focus. So this is relative to this focus. Third, we have this ray number 3 goes along a line through the center of curvature C, and it reflects back along the same line as shown. This one. Next is to trace the reflected rays, and the point of intersection is the position of the image. So for this case, this after getting the point of intersection of our reflected rays, we have this image. And this image for the case of convex mirror, so this is always smaller than the object, as can be observed. It is upright, and this is virtual, meaning that it is placed at the opposite side of the reflected rays. Next, let's try a concave mirror. Initial step is to place the object on the principal axis in front of the mirror. Mark the important parts, including the center of curvature C, principal focus F, and the point P. These labels, again, will guide you in your ray tracing. First step is to draw a line from the top of the object going to the focus. And this will generate this reflected ray parallel to the principal axis. Second, draw another line, this time parallel to the principal axis and from the object, going to the surface of the mirror. For the concave mirror, such as this parallel ray will be reflected towards the principal focus F. Okay. Third, so ray number 3, this goes a line through the center of curvature C and reflects back along that same line, as can be observed in my drawing. Now, tracing back the reflected rays, the point of intersection is the position of your image. And for this case, note that for concave mirror, image characteristic depend on the object distance. So it varies depending on your object distance. And for this case, wherein the object O is beyond C, we have the following. So the image form is real, given that it is on the same side with your reflected rays. This is inverted, this is smaller, and this is formed between C and F. As I have said previously, the image characteristic for the concave mirror depends on the object position, and I have here 6 cases. First, when the object is placed between F and P, such as this one, and doing the ray tracing, we will have the following characteristics. So this is virtual, your image is formed here. Then this is upright, this is larger, and the image is behind the mirror. Now, when the object is placed at point F, or this one, the principal focus, we will observe the following. So the image will be formed at infinity. So that's why we have this parallel line as we trace back our reflected light rays. So this line did not intersect. And the image characteristics, so this is virtual, this upright. It is larger, but the image is formed at infinity. Now, when the object is placed between F, the principal focus, and C, we will have the following image characteristic. So the image is real, it is inverted, it is larger, and formed beyond C. Now, when the object is placed at point C, we will have the following image characteristics. First, it is real, formed at the same side of your reflected rays. It is inverted, same size, and the image is formed at point C as well. Next case, this is the 5th case, when the object is placed beyond C. And we will have the following characteristics. First, it is real, it is inverted, it is smaller, and the image is formed between C and F. Last, when the object is at infinity, so that's why we only have this parallel light rays, we can observe that the image form has the following characteristics. So first, it is real, it is inverted, smaller, and the image is formed at the principal focus F. Now, we can use this equation derived through geometry in finding the position and size of the image. So this equation, so 1 over d naught, wherein d naught is the distance from the object to the mirror, plus 1 over di, di is the distance from the image to the mirror, is equal to 1 over f. Your f here is the focal length of the mirror, which is equal to the half of dr. Note that d naught and di are positive if the object or image is in front of the mirror, and negative if it is behind the mirror. A positive image, shown here, means the image is real and inverted, while negative when the image is virtual and upright. The focal length f is positive for a concave mirror and negative for a convex mirror. Next, we have this expression for the magnification. So m is equal to the image size over the object size, and this is equal to di over d naught. Note that when your m is positive, it means you have an upright image, and when your m is negative, you have an inverted image. Next, we will discuss lenses. Lenses form images by refraction, where incoming light is bended. When we say refraction, It means the direction of light change when it passes through two materials of different optical density. So it means that they have different index of refraction. And this is caused by the change in the speed of light as it passes through two materials with different index of refraction. Lenses can be classified into two. So first, we have the convex lens. These lenses are also known as converging lenses. It is thicker at the center compared at the edges. Next, we have the concave lens. And these lenses are also known as diverging lenses. It is thinner at its center than the edges. Still for the convex and concave lens, so let's start first with the convex. Parallel rays close to the principal axis are refracted inwards as shown and converge to the focal point capital F of the convex lens. On the other hand, parallel rays close to the principal axis are refracted outwards and appears to diverge from a focal point as shown of the concave lens. And please note also that lens has two focal points, one on each side, each a distance f from the midpoint, assuming we have the same medium outside. Okay, now let us talk about the construction rules in ray diagram for convex lens. First, any ray parallel to the principal axis, so the one in the yellow and the green is the principal axis, will be refracted through the focal point F shown. Second, any ray passing through the focal point F, this one, will be refracted parallel to the principal axis. Last, so third, any ray passing through the optical center C will not be refracted as illustrated here in violet. Similar with your concave mirror, we have different cases as well to describe the image characteristic for the case of convex lens. Note that it is dependent on the object distance. Here, I will refer to this variable u, and the variable v refers to the image distance. So for the case when your u is less than f, as shown here, so this is our object, we have the following characteristic. So the v, the image distance, is greater than u, and the image form here is virtual, so it is on the opposite side of your refracted rays, which is this one, and it is upright, it is larger, and the same side as the object. Second, when your object distance u is equal to f, we have the following image characteristic. Your v, or image distance, is at infinity, as shown, so we don't have any intersection here, and the image is said to be virtual, it is upright, it is larger, and the same side as the object. Next, third, for the case wherein the object is placed between f and 2f, as shown, we have the following image characteristic. So first, the v, or image distance, is greater than 2f, so we have here, then it is real given that the image is formed on the same side with your refracted rays. It is inverted, it is larger, and at the opposite side of your object. Next, when the object is placed at 2f, we have the following characteristic. So the image is formed in v is equal to 2f. It is real at the same side of your refracted rays. It is inverted, same size, and opposite side of your object. Fifth case, when the object is placed greater than 2f, this one, we have the following. So the image is formed between f and 2f. It is real, it is inverted, smaller, and opposite side of the object. Last, when the u is at infinity, we have the following. So the image is formed at f. It is real, inverted, smaller, and opposite side of the object. Now, we have here the construction rules for the ray diagram of a concave lens. First, any ray parallel to the principal axis will be refracted and appear to come from the focal point F. Second, we have this one. Any ray passing to the focal point F will be refracted parallel to the principal axis. Third, any ray passing through the optical center will not be refracted. No matter where we place the object, for the case of concave lens, we have this same characteristic. The image is virtual because it is located at the opposite side of the refracted rays. This is the refracted rays. Virtual image can be seen but cannot be captured on a screen, or it does not form a visible projection on a screen. Now we can derive an equation to find the image size and location using simple geometry for the case of lenses. So for this scenario, I have the similar triangles A prime O, and C prime O. Thus, we have H prime, the ratio of the height, is equal to U over V, this one, the object distance and the image distance. And we also have this similar triangle BOF, so BOF, and this triangle C prime F. Thus, we can also write H over H prime is equal to F over V minus F, or this distance and this distance. Now, by manipulating those equations, we can have this final form. 1 over U plus 1 over V is equal to 1 over F. This is the lens equation. This is the same form as the mirror equation. I just changed the variable from D naught to U and DI to V. This describes all the possible arrangements, but take note of the sign convention. Okay, so this is the lens equation, and take note that the front part of the lens is the side from which incoming light rays will enter. U is positive if the object is in front of the lens, negative if it is at the back of the lens. And V is positive if the image is at the back of the lens, and negative in front of the lens. Lastly, F is positive for converging lenses and negative for diverging lenses. Similar with the magnification for mirrors, you also have your M magnification for this, and this is equal to negative V over U. And please take note of this sign convention. Now, we also have this expression for the focal length F of thin lens in terms of the radii of curvature of the surfaces. If the curvatures have front and back surfaces R sub 1 and R sub 2 respectively, and thin lens or lens is in air, then the lens maker's formula can be used. If the center of curvature is in back of the lens, R1 and R sub 2 are positive, while negative if it is not in front. And here, this one, is the index of refraction of the lens. Okay, in summary, light can be manipulated using mirrors and lenses. The law of reflection is useful in identifying the image formed using mirrors. Lenses form images by refraction or by bending the light. Object distance, image distance, and focal length are mathematically related in describing image formation. And that's it for this lecture. Thank you.